equation of motion, and the methods to solve those equation of motions. And today um, we will be looking at damped and undamped vibration in single degree of freedom system. So uh, we'll be looking at damped and undamped vibration in single degree of freedom system again, and but this time systems are subjected to harmonic forces. So previously, if you guys remember, our equation of motion had taken this form: mu double dot plus ku is equal to 0, and we called this as our homogeneous equation because there was no external force applied on the system. But right now we will be looking at this equation: mu double dot plus ku will be equal to some kind of external force, which is P of T. Now this is a non-homogeneous equation, ordinary second order differential equation, and we want to solve this equation and determine the value of this displacement with respect to time. We don't mind knowing the value of velocity and the value of acceleration during the course of vibration. So how do we do that? First, we need to define the type of dynamic loading. So we will come up with the most simplest form of dynamic force, which is varying with respect to time, and that would be either in the form of P naught sine omega t or P naught cos omega t. The shape of both these forces is harmonic. So this is P naught sine omega t, and this would be equal to P naught cos omega t. Now P naught is the amplitude of this force, and this sine omega t and cosine omega t basically helps this P naught to achieve its maximum value. So at time t equals 0, if for example this axis is our time axis and this is our P of t axis, then when time is equal to 0, then the force will be equal to 0, and then eventually it will take the maximum value of P naught at some time interval. Now you will see another omega term here. This omega is basically the frequency of the force. It is different than omega n. Omega n was equal to square root of k divided by n, whereas this omega, which doesn't have any subscript n with it, describes the variation of loading with respect to time. Now, a harmonic force is one whose variation, which with time is defined by any one of the following equations, where P naught is the amplitude or maximum value of force, and omega, which should not be confused with omega n, is its frequency. So omega is the frequency of the force, also called as exciting frequency or forcing frequency. And we can determine the time period of this forcing frequency given by this formula: T equals 2 pi divided by omega n. Once again, this is not the natural time period of the structure. This is not Tn. Okay, this is the T without any subscript. This is the exciting period or forcing period. And if you want to determine the total time period of this forcing function, you need to see where this function is repeating itself, and that is going to be, that interval is going to be the time period of the structure. So this is our time period of the forcing function. Now the equations used in this module are strictly applicable to P naught sine omega t. Okay, so we will take just the most simplest form of force, and we will solve all our equations according to this force now. Um, Now, what are the harmonic forces and what are the origin of all these harmonic forces? A common source of such a sinusoidal force, that is P naught sine omega t, is unbalance in the rotating machine, such as the turbines, electric motors, and electric generators, as well as fans or rotating shafts. So whatever component is rotating and has an unbalanced mass attached to it, it's going to cause some kind of harmonic force which will take the shape of P naught sine omega t. Unbalanced cloth in rotating drum of a washing machine is also a harmonic force. When the wheel of a car are not balanced, okay, so all those students who are drivers as well, they will know this thing. Harmonic forces are developed in the rotating wheels. If the rotational speed of the wheel is close to natural frequency of the car suspension system in vertical direction, amplitude of vertical displacement in car suspension system will increase, and violent shaking occur in the car due to match of frequency of the force. Due to vertical component of harmonic forces acting at unbalanced mass center, with natural frequency of car suspension system in vertical direction equal to omega n. So we have two different omegas. One is omega n, shown here. Um, and we call this as our structure's natural frequency. This is omega n, and then we have this omega, which is the forcing frequency. Now, how will the structure responds to these harmonic forces? The equation of motion for harmonic vibration of undamped system can be given by this equation here. Now, we can see that this is a uh, non-homogeneous ordinary second order differential equation, and so it will have two solutions. One will be the particular solution and second is the complementary solution. The solution to equation of motion is made up of two parts. The first part is the solution which corresponds to forced vibration and is known as the particular solution of the ODE. The corresponding vibration is known as steady state vibration, for its present because of applied force, no matter what the initial conditions might be. So, for example, if the initial conditions are zero, means there is no displacement to begin with, and there is no velocity to begin with, even then the structure will have these vibrations because of the presence of this forcing function P naught sine omega t. The second part is the solution to free vibration, which does not require any forcing function. This part is known as the complementary solution, and the corresponding vibration is known as transient vibration, which depends on the initial conditions only. So whenever you are solving these kind of equations, you will solve first for mu double dot plus ku equals 0, and you will find the complementary solution. And once you have done that, then you will start with the uh, particular solution or steady state vibration. Now we don't want to really go into the solutions. We will get to the final form, and the final form of this equation, mu double dot plus ku equals p naught sine omega t, will have the particular solution of p naught by k 1 divided by 1 minus omega over omega n square into sine omega t. Once again, you should notice that this omega is the forcing frequency, omega n is the natural frequency, and this sine omega t, this thing represents the variation of p naught with respect to time t. Now, you should also keep in mind that in this scenario, omega is not equal to omega n, because if omega is equal to omega n, then you will have 1 minus 1 situation, and eventually this will grow to infinity or undefined number. Now, let's, for simplicity's sake, since this omega, which is the forcing frequency, this is a constant number, the omega n is a constant number, so we will term it as a frequency ratio. Omega divided by omega n is termed as frequency ratio, and we will call it as RW. We will use RW in our lectures to represent this ratio here. So again, this simple equation, the particular solution, will reduce to this newer shape P naught by K, 1 divided by 1 minus R omega square. And once again, omega must not be equal to omega n for this formula to be valid. Now, UP is the displacements. What is this displacement? This is the displacement corresponding to the particular solution, that is due to forced vibration only. What if there is some initial displacement as well? For example, before the application of this load P naught, we have also displaced the structure to some some new position. then in that case, the complementary solution of undamped vibration is given by this famous formula that we discussed in our previous class, A cos omega nt. Now, look at this omega n. This is the natural frequency of the structure. This is square root of k by n. And b sine omega nt, this is also square root of k divided by m. UCT is the displacements corresponding to the complementary solution that is due to free vibration and depends on initial conditions only. Now, what will be the total solution? As we might have judged, your total solution will be equal to the complementary solution plus the particular solution. So you need to add these two, and this is because of the law of superposition. Since the system is elastic, so you can just add these two quantities together. So when you do that, you will get the total solution, which is going to be equal to A cos omega nt plus B sine omega nt. Again, this is our transient solution, and then this is P naught by K, 1 divided by 1 minus R omega square into sine omega t, and this part is because of the external force P naught sine omega t. Now, still we need to determine the value of A and B in let's call this equation 1. And for that, we need two initial conditions. One is the displacement when time t equals 0, and we need velocity, initial velocity when time t equals 0. So if you put all these values in equation number 1, you will get u naught cos omega nt plus u naught velocity by omega n minus p naught by k r omega divided by 1 minus r omega square sine omega nt divided by plus the steady state solution, which is the same p naught by k, and this is because of the externally applied force. Now, what happens if our initial displacement and initial velocity, both of them are 0? The structure starts vibration from its initial condition or initial conditions at which the velocity is 0 and the displacement is also 0. In such case, the complementary part of solution given on previous slide specializes too. So let's see, this whole term will vanish here because the initial displacement is 0 and the velocity term is also 0, and so you will have only this part in the transient solution, and you will have this remaining part as the complement or as a steady state solution. So our equation will reduce to this form. Okay, you have this 0 displacement, you have the velocity, initial velocity is 0. So complementary solution will reduce to this, and the total solution will take this specialized form. P naught by K, 1 divided by 1 minus R omega square, U omega t. Again, this omega is the forcing function, R omega sine omega nt, and this is the omega of the forcing of the structure itself. This is square root of K divided by N. And so this is the total solution. If force is applied slowly, when the acceleration is 0, this is the definition of our dynamic forces, that if the force is applied at such a speed or at such a rate that it causes acceleration in the mass, we call it the dynamic force. But if it is unable to cause acceleration in the structure, then we can say that it's a somewhat static kind of force. So let's say if acceleration is 0, this whole term will vanish and you will have ku equals p naught sine omega t. And so since there is no acceleration in the system, therefore your total displacement will be equal to p naught by k sine omega and omega t. Now, if you look at this thing here, P naught by K, this represents the famous formula P is equal to K times delta. So whatever is the deformation, that deformation is because of the force. When you have a structure whose stiffness is finite and is known, and so the structure will deform corresponding to the stiffness of the system. The subscript ST standing for static indicate the elimination of accelerations effect. So the maximum value of deformation or static deformation can be interpreted as the deformation corresponding to amplitude of P of the force P naught. So U static naught is equal to P naught K. So this is over static displacement, and this static displacement is varying with respect to sine omega t thing. It would be worth mentioning that if you have a structure like this, for example, and it has a known value of stiffness, and so if you apply the force as P naught sine P naught sine omega t. What does it mean? It means that this force is changing its direction according to this formula. Now, if you apply this force really slowly, what will happen is that the structure will first move to this new position, and then after some time, the structure will go back to its other position. But it will follow the trend of the forcing function itself. So if this is over P of t, then this will be over U of t. And if you look at this thing here, whenever there is a peak in the force, there is a peak in the displacement as well. And when there is a negative force, then there is going to be a negative displacement. So this is a static kind of displacement, and maximum possible displacement is going to be equal to P naught divided by K, since sine omega t takes a value between 1 and minus 1. So U particular will be given as P naught by K, 1 divided by 1 minus R omega square sine omega t. And now we need to change this P naught by K, and let's write it as static displacement. So particular solution or particular displacement is equal to the static displacement multiplied by this whole term here. Now, if you look at the sine omega t, this is a pretty simple function to understand and to comprehend, but this bracket is rather difficult to imagine. Okay, it has three conditions. For example, the simplest one would be when r omega square value is equal to 1. And so the particular displacement or this displacement is gonna shoot to infinity. You will have a very large displacement, and we call this as resonance condition. What is resonance condition? When the natural frequency omega n will become exactly equal to the forcing frequency omega. So when omega n is equal to omega r, omega square value will be equal to 1, and the displacement will shoot to infinity. Now it can be observed from this equation that UPT has negative sign when frequency ratio r omega is greater than 1. That is, the frequency or the forcing frequency is larger than natural frequency of the structure, and vice versa. A graph on next slide is plotted between the frequency ratio r omega and the this bracket term here. Okay, and we haven't called it anything because we want to understand what this value in the bracket is doing with the displacement. So if you look at this graph here, the horizontal axis is r omega. It's the ratio between omega to omega n, and the vertical axis is some kind of amplification. Okay, and if you look at this value here, this is equal to 1. So what does it mean? It means that when forcing frequency r omega is equal to 0, or omega is equal to 0, which basically means that omega is equal to 0, then what happens? What happens is that this whole term, um, what it means is that you will have this as total particular displacement, and so your structure is moving very slowly and doesn't have any of the dynamic components to it. Otherwise, if omega n is infinity, means the structure is very, very rigid. Even in that scenario, our omega is going to be undefined, or if we take it as 0, then our displacements are going to be equal to 1, means the amplification is 1. Now, if you look at this diagram all the way up to probably up till here, these values are very close to 1. What does it mean? It means that for a smaller value of r omega, we can surely assume that structure is displacing um, uh, as a rigid body, or it is displacing as um, as a static displacement, and it does not have any kind of amplification. But beyond about 0. 0.2, if you look at 0.5, now the amplification has grown manifolds, and near 1 it has asymptotically reached to infinity. Now, as soon as our omega value crosses this threshold of 1, means it has crossed the resonance conditions, the amplification turns into negative direction, and then it steadily converges towards the 0 point. All this portion before 1 is known as in phase displacements, and all the values after 1 are the out of phase displacements, out of phase displacements. Okay, what does it mean? It means that the structure in during the in phase region, the structure is displacing along the direction of the applied force, and out of phase means that the force is changing slowly, and the structure is is displacing against the direction of the force. It is summarized here. Following observations can be made from the plot given on the previous slide. When R omega is less than 1, means the structure is in phase, the displacement is positive. Okay, displacement is positive, indicating that UP, a particular solution, and the applied force has the same direction. The displacement is said to be in phase with the applied force. When R omega value is greater than 1, omega is greater than omega n, the displacement is negative, indicating that the ut and pt has opposite direction. Means if the force is applied in the horizontal direction, the displacements are in the opposite direction, okay, which is not so intuitive, because our physics says that when you apply the force, the structure will move along the direction of the force. The displacement is said to be out of phase with the applied force. Now, here is a situation. If you look at the diagram number 1, you will see that the structure has moved to horizontal direction. So this is our direction of displacement. Um, and the P naught sine omega t is also in the same direction. And so we say that this is the omega over omega n is less than 1. But if you look at this diagram number B, the structure has finally moved to a newer position, but the force is still applied in the same direction. Okay, so we call this out of phase displacement. Um, let's check this video out. Here. Now, if you look at this mass here, um, what it shows is, so this block is mass here, and if you look at this connection, this is the elastic spring or the rubber band, which is bringing the structure back to its position. So let's start a little bit of vibrations. So this is the mass, this is the band, and if he moves his hand very slowly, okay, not so slowly, he's giving initial displacement to the structure, and so this is over omega n. This is the omega n of this mass and spring system. In phase 2, he's gonna move his hand in the upward and downward condition, and this replicates P naught sine omega t conditions, and let's see how the structure behaves. Right now, P naught omega, which is the forcing frequency, is very small. So structure is moving with the externally applied force. It doesn't have any kind of excessively large deformation. It is deforming according to the um, displacement of hand. Now let's move this hand a little bit faster, and now you can see that your displacements have drawn manifolds. It is greater than the static displacement, and now let's increase the frequency again, and now this has gone out of phase. Okay, this force is applied uh, pretty fastly, but the structure is not able to respond according to that. And so we call this as our um, out of phase displacement. Now, deformation response factor, or RD. So in our previous slide, we came up with this solution, with this particular solution, and we will see its implications in a while. So P naught by K, 1 divided by 1 minus R omega square sine omega t, and P naught by K, as we decided earlier, is going to represent the static displacements, and then the same formula again. This equation can be rewritten as up is equal to the static displacement multiplied by sine omega t minus phi, or u static multiplied by the some kind of dynamic amplification factor, or RD factor, multiplied by sine omega t, where RD is basically equal to the static dynamic displacement to the uh, ratio of the dynamic displacement to the static displacement. So let's assume that this is our dynamic displacement and this is our u static. So if you multiply, if divide both sides by u static, you will get 1 divided by 1 minus r omega square into sine omega t. The sine omega t value changes from -1 to 1, so it really is not of much significance here. So if you look at this angle, we have two conditions only. When phi is equal to 0, we say that omega is smaller than omega n, and r omega will be smaller than 1. When phi is equal to 180 degrees, then omega will be greater than omega n, and r omega value will be greater than 1. What is important is this RD thing. RD is the dynamic magnification factor, or deformation response factor, where u naught is amplitude of dynamic displacement and phi is over phase angle. So if you look at this RD value, it basically tells us that our dynamic displacement is going to be this time larger than the static corresponding static displacement. So this value can be greater than 1, it can be equal to 1, and it can be smaller than 1. Now, if you plot the value of RD, 1 divided by absolute value of 1 minus r omega square, you will get a curve which looks like this. Okay, so this is our RD value, this is our u dynamic divided by u static value, and horizontal axis is our frequency ratio, or omega. Nearly quasi-static response till all the way up to 0.2 or W. Load may be defined as quasi-static. Quasi-static means that it really is not static, but um, it appears to the structure that it is static. Now all the values of r omega on the left hand side of 1 show the in-plane condition, in-plane displacements, and all the value to the opposite sides will show that these are out of phase displacements. Okay, now if you look at this one line, this red line, it means that this is our static deformations. And so if you look at all these values, it means that the deformation is greater than static deformation. So for instance, if r by r omega value is here somewhere, then your dynamic displacement is going to be equal to 3.5 times larger as compared to the static displacement. So if you have the static displacement of 10 inches, the dynamic displacements are going to be 35 inches. Now, as soon as you reach the out of phase conditions, means r omega value is greater than 1, the amplification factor reduces drastically, and then at certain point, at about square root 2, when r omega is square root 2, your dynamic displacements once again are equal to your static displacements. And when you move beyond square root 2 value, then your dynamic displacements are smaller than your static displacement. What does it mean? It means that, for example, if your R omega value is at 2, then if your static displacement is 10 inches, then dynamic displacements are going to be equal to 5 inches. It's about half of this. And so theoretically, if R omega value is infinity, then the structure will not vibrate at all. Okay, the ground will shake, you will have externally applied force, but the force is changing so randomly that structure is unable to comprehend, it is unable to cope with that kind of change. And so you will not see any kind of vibrations in the structure. Now, following observations can be made from the plot itself. When R omega is small, that is, force is slowly varying, RD is only slightly greater than 1, or in other words, amplitude of dynamic deformation U naught is almost same as amplitude of static deformation. So static and dynamic displacements are the same. When R omega value is greater than square root 2, and the dynamic deformation amplitude is less than the static deformation. Okay, so for R omega value greater than 2, dynamic displacements are smaller than static displacements. When R omega increases beyond square root 2, RD becomes smaller and becomes 0 as R omega tends to infinity. When R omega is close to 1, RD is many times larger than 1. And this is the resonance conditions, the so-called resonance conditions, and we want to avoid these conditions at all cases. Now, let's see a numerical. A video camera of mass 2 kg, the mass is given of this video camera, this is 2 kg, is mounted on top of the bank building for surveillance purposes. The video camera is fixed at one end of a tubular aluminum rod whose other end is fixed to the building as shown. So this is a cantilever structure. 3EI over L cube is the stiffness of this structure. The wind-induced force acting on the video camera is found to be harmonic with Pt equals, this is going to be over P naught, which is 25, and sine 75 is over omega, so 25 sine omega t newtons. Determine the cross-sectional dimensions of the aluminum tube if the maximum amplitude of vibration of the video camera is to be limited to 0.005 meter, and modulus of elasticity of aluminum is 71 gigapascal. So let's go and check the solution of this problem. We'll open it as read only. And so this is our solution. Okay, so solution takes the form of something like this. Let's draw the diagram first. This is our diagram. Okay, so this is the cantilever structure. There's a mass of 2 kg probably, and force is applied in this direction. Now we know that U static dynamic displacement by static displacement is given by R omega, and this is equal to 1 divided by 1 minus R omega square thing here. The dynamic displacements are limited to 0.005. Okay, so this is already given, and we are asked to determine the static we are asked to find the cross-sectional dimensions of this aluminum tubular rod. So putting the value in equation above, we will get U static equals P naught by K. P naught is already given as 25 by K. If you remember, P of T was equal to 25 sine of 75T. Okay, so this thing here is our P naught. So 25 divided by K is U static. R omega is omega by omega n. Now omega is 75 is given in the forcing function thing, and omega n needs to be determined, which is equal to square root of K by m. Now value of K is unknown because it is largely dependent on the cross-sectional dimensions that we need to determine. However, the mass is given as 2 kg. So R omega value will come out to be 75 square root of 2 divided by square root of K. Now we have this as our equation 1. Sorry, this is our equation 1, and this is our equation 2, let's call it, and this is our equation 3. So this value will come from equation 3, and this value will come from equation 2. Put all these values in equation 1, you will get this equation this fancy equation here. After rearranging, you can see that we have one equation and there is only one unknown, which is the value of k. So after rearranging, you will get the value of k equal to 16,250 Newton per meter. Now we have realized that the structure is a cantilever structure, so so the stiffness should be given by 3 EI over h cube. The k value is already determined in the previous step. This 3 comes from the formula. This is modulus of elasticity. Moment of inertia needs to be determined, and this is our height. So moment of inertia comes out to be 9.54 into 10 power minus 9 meter power 4. In our last step, we need to find the value of diameter. So moment of inertia will be equal to pi d4 by 64. So by this method, we will get the value of d, and this is the going to be the diameter of the pole itself. So then we move on to our more complicated form, which is response of damped um, system under harmonic forces. So in previous 18 slides, we studied about undamped systems, and now we will carry on with the damped thing. Now, as you can see, our equation of motion will take this new form, mu double dot plus cu dot plus ku equals p naught sine omega t. Again, it's a non-homogeneous ordinary second order differential equation. So it will have two solutions, the complementary and the particular solution. Um, Initial conditions are already given, and so the particular solution of the differential equation will take this form: u of pt equals c sine omega t. Again, this is the forcing frequency thing, plus d cosine omega t. The value of c and d can be determined using ordinary mathematical formulas, and they should boil down to this thing. Okay, so this is the value of p and this is the value of c. So when you put these values back in your equation number one, you will get the solution, the total particular solution, the particular solution only. Once again, the complementary solution is given by u complementary t equals e power minus zeta omega nt. Now this component or this form is because of the initial conditions only. So since it depends on initial conditions, so we will have the omega n, means the properties of the structure itself, which is equal to square root of k divided by n, multiply by, in the bracket, you will see a cos omega dt plus b sine omega dt. The values of a and b are to be determined using the initial conditions. Now, the complete solution to this form, the complete solution to over this equation A is um, is something like that: e power minus zeta omega nt a cos omega dt plus b sine omega dt. This is the transient solution, and then the steady state solution, which depends on the force only and is not dependent on the initial conditions, is c sine omega t plus d cosine omega t. The value of a and b needs to be determined from initial conditions, and value of c and d have already been determined in previous slide. Now, if you look at the total solution, it is going to be something like that. The wiggly curve is the total solution, and it has two parts. The more wavier form, the more disturbed form, is your um, transient solution, and the more smooth curve is your steady state response. The transient response, difference between the total response and steady state response, diminishes after a few cycles because it has very high damping ratios and has very high frequency as compared to the steady state. So eventually it's gonna die out. That is, u total will eventually be equal to the particular solution, means whatever is the externally applied force, the total displacement will follow the trend of that applied force, and as u complementary will tend to zero. So till up to about this point, your total solution, u total, will be equal to u complementary plus u particular, and beyond this time, you will have u particular only. UP only, and UC will vanish out. The steady state deformation can be rewritten as we discussed previously as a particular solution is equal to the dynamic displacement multiplied by sine omega t minus phi, and where dynamic displacement can be rewritten as static displacement multiplied by the displacement amplification factor RD. The RD is as compared to our previous case takes a very complicated form, and the new formula for the damped system is going to be something like this: 1 divided by square root of 1 minus r omega square whole squared plus 2 zeta r omega squared. Now we will be interested in determining the amplitude of displacement with respect to the frequency ratio. So this is our new graph. If you look at the graph number one, this is for zeta equals 0, means there is no damping. It's an undamped system, as we discussed in previous slides. And then for 1% damping, 10% damping, and 20% damping. Now there are three phases. If you look at this graph closely, one would be somewhere here. Okay, between this thing, the damping doesn't play much of a role. All these curves are very close to each other, and there is no clear demarcation between the response of 10% damped structure to 20% damped structure. After about at this point, the damping is ineffective once again. Okay, it's not effective, and between these 2 points, the damping plays very important role. So as such, the damping has a limited use when it comes to the frequency distribution of the system. Now, what does it mean? Let's go back and check our um, animations again. We have seen this famous test over and over again now, in which you have a shake table, and on the top of shake table you have three different structures. One is very flexible, the taller is very flexible, and then there is an intermediate structure, and then there is a short structure, and all these structures have different frequencies. Now let's start our shake table at frequency ratio of um, very small or 0, and as you can see, the shake table is moving in the horizontal direction. So are the masses are moving as rigid blocks, and so this corresponds to your rigid body displacement, or let's call it static displacement. Now we will increase the frequency of this shake table and see what is going to be the total response of the structure. Now the frequency has increased, and the total displacement of the most flexible structure has increased as well. Now look at the dynamic displacement. This is at about 4 hertz, you will see maximum deformation. This is the resonant. And now um, this structure is vibrating violently. It's at the resonant condition, means the frequency of the shake table and frequency of the structure is the same. R by R omega value, R omega value is equal to 1. And now the frequency has increased. So this structure has gone out of phase, while this structure is getting close to its resonant conditions. Now, since this structure, the taller structure, has gone out of phase, you will see the displacements have ceased rapidly, and eventually it will appear that there is no dynamic displacement in the structure at all. So this is shaking violently at about 6.35 hertz. This is now at resonance conditions. And now we have increased the frequency even to a bit further. Now the tall structure doesn't seem like vibrating at all, while the rigid structure, the smaller structure, is vibrating, and so its frequency is going to be at 11 hertz. But look at the response of the flexible structure at frequency of about 11 hertz. You will not see any displacements here or here. So let's check our formulas and graphs and see where do we stand. So we stand somewhere here. The tall model has a natural frequency of about 4 hertz, and when subjected to forcing frequency of 4 hertz, you will see our omega value to be equal to 1. So we will have resonant condition at this point. But when the medium structure is vibrating at resonance condition, you will see that its frequency is 6.35 hertz. The forcing frequency is 6.35 hertz, but as compared to the tall structure, the frequency ratio between the tall structure and the medium structure is going to be 1.59. And so let's check over this graph again. Okay, so this is over our d-axis and horizontal is over our omega axis. So, let's assume that we have about 10% of damping. So let's take this graph here. So at resonance condition, R by R omega value will be equal to 1. Um, R by R omega value will be equal to 1. And so your maximum amplitude is going to be about 5 times of static displacement. This is static displacement, and this is our dynamic displacement. So if this is 3, here somewhere it will be 4, and this point will be 5 on this graph here. Now, when we have the resonance conditions for the medium structure, the tall structure will have R omega value of about 1.59. 6.35 is the natural frequency of the structure when it's vibrating. 4 is the natural frequency of the tall structure. So at about 1.59, your the tall structure will have 0.7 or 70% of the static displacements. Um, as compared to at rest conditions. So for the short structure, the natural frequency of the short structure is 11.35 hertz. When this structure will be vibrating, the stall structure will have R omega value of about 2.84. And so it will have vibrations of about 15% of the um, static displacements. Here are the comments. Tall model resonant frequency of 4 Hz. When exciting frequency for tall model is 6.35, R omega is 1.59. And similarly, when exciting frequency is 11.35 Hz, means when the short structure is vibrating, R omega will be equal to 2.84. Both the above mentioned R omega values are greater than 1, means the structure is out of phase, and so there will be a de-amplification of the system, and also greater than square root of 2, showing reduction even in static deflection, that is approaching stationary position, especially at 2.84 hertz. For system with zeta greater than or equal to 1 by square root 2, the static deformation or continuously decaying towards stationary position. So let's check the value of R omega equals 2.84 in the video again. And the taller structure should be at rest conditions. Okay, so here we have the medium structure vibrating, and now look at this structure, the taller structure. It has R omega value of 2.59 almost, and it is not vibrating. It is vibrating at about 15% of static displacement, which is very small as compared to the short structure here. Now, following observations can be made from the plot. Okay, let's talk about our findings now. Um, Damping reduce RD for all values of frequency ratio or omega. However, rate of reduction highly depend on the magnitude of R omega, around zero point 0.5 to 2. If R omega is around 0 0.2 and below, that is, force is slowly varying, RD is only slightly greater than 1 and thus unaffected by damping at all, as seen in our previous curve here. So you can see that all these curves have a unique value. They are very close to each other, and so the displacement is unaffected by the magnitude of damping. If the R omega is value is very high, around 2 and above, the force is rapidly varying. RD tends to 0. In other words, RD is unaffected by damping again, and U naught can be approximated as U naught is approximately equals to P naught divided by M omega square, where this omega is the ratio of the forcing frequency. If the R omega is approximately equal to 1, means the resonant condition, then the amplification factor will be given by this formula here. At exactly R omega square equal to 1, the RD value is only dependent on zeta value, and this is going to be 1 divided by 2 times zeta. This means that for a system with 5% of the critical damping, the maximum displacement of dynamic response is 10 times the equivalent static displacement. And so the total displacement will be equal to static displacement divided by 2 times zeta. After rearranging, you can rewrite this whole formula as the dynamic displacement is equal to P naught divided by C divided by omega n. So dynamic displacement will depend on P naught. It will depend on the structure and its stiffness and mass ratio, and then you will have the value of C here. So with that, we will come to our problem number 5.2, an air conditioning unit weighing 1200 pound. So this system weighs about 1200 pound, and it is placed at the middle of two parallel simply supported steel beams. And so these beams will deform as such like this because of the weight of air conditioning unit. The clear span of the beam is 8 feet, so 4 feet and 4 feet, and this air conditioning is right in the middle of these two beams. The second moment of cross-sectional area of each beam is 10 inch power 4. The motor in the unit runs at 300 round per minute, and we have to convert this into revolution per seconds or hertz and produce an unbalanced vertical force of 60 pounds. Okay, so this 60 pound is basically over P naught. Neglect the weight of the beams and assume 1% viscous damping. So this is our assumption. In the system for steel, modulus of elasticity is 30,000 ksi. Determine the amplitude of steady state deflection. So we will go to our solution form and see how it's gonna go. So this is problem 5.2. All the values are given. In damped system, U particular solution dynamic displacement is almost equal to our total dynamic displacement, and this is given by the formula here. RD is equal to 1 divided by square root of 1 minus R omega square whole square plus 2 zeta R omega squared. Data is given as such. Weight is 1200 pounds. Modulus of elasticity is given. Moment of inertia is 10 inch power 4. Length is 8 foot. Zeta is 1%. P naught is 60 pound. And revolution omega is 300 round per minute. Can be converted to 5 revolutions per second. U static is P naught divided by K, but we don't know the value of K. So for that, first we know that this system is springs in parallel, and so total stiffness or effective stiffness is going to be equal to K1 plus K2, since both the moment of inertias and material and rest of the dimensions are the same. So K1 is equal to K2, and so we can rewrite this formula as 2 times K1. So stiffness of a simply supported beam when load is point load and is applied at the center of the beam, then our stiffness formula will be 48 EI over L cube. For the two beams, we will multiply 2 with it. After putting all these values, E, I, L, we will get stiffness of 39, 390, 625 pound per feet. Our omega value is given by this formula here. The frequency of the force divided by natural frequency of the system. And so it will be equal to 10 pi divided by 104482 square the root. Or omega will come out to 0.31. Now we can go back to our equation number one. We have values for U static, we have values for our omega and zeta, and so we will put all these values here, and our dynamic displacement will come out to be equal to 1.69 into 10 power minus 4 feet. We can convert these values into inches or millimeters as you desire. With this, we will conclude our today's lecture, and in a hope that um, when we come back, we will start from where we left. If there are any questions, you may ask now.